So let's talk about derivatives of functions of more than one variable. If someone were to ask you, what's the derivative of a function with one variable? Your mind goes back to Calc 1 where you think about the slope, which gives you the rate of change along the x-axis. Well, now with functions of more than one variable, say two variables, the slope is not such a simple concept because you get a whole wide variety of slopes depending on which direction you're talking about for a particular point. But we can still talk about the rate of change along the x direction. We capture this concept using the partial derivative. So the partial derivative of f with respect to x at the point AB is defined by this limit, okay? And it sort of reminds you of the limit of the, that gives the definition of the derivative for a function of one variable. For example, here we have so this is the definition of the derivative for a function of one variable at the point x. And you could see the similarities with the definition of the partial derivative of a function of two variables given over here. Now, something to notice that the x, you have a plus h where the x value that we give to this function is. So we have a plus h minus f at ab So this is then the function at the point AB, but we move along the x-axis to the point A plus h in order to get our secant line, while B, the value that goes in for y, stays fixed. So you give the function here on the left-hand side B for the y value, and you also give B for the y value on the right-hand side. But x is allowed to vary, okay? What you're getting by this is that x is allowed to vary, but h stays, y stays fixed at b, and we seek the ratio of f at a plus h b minus f at a b all over h, okay? So we have a kind of, it's similar to what's going on with functions of one variable, if you keep in mind that we're keeping the y value fixed at b. We could also do a similar thing with respect to y. Here we let the y value now vary. So we have y at b plus h, and we subtract that. We subtract fab from that value. So we get secant lines by varying y, and x stays fixed at a throughout this process. And so this here gives you this ratio, once you take the limit as h goes to 0, gives you the partial derivative with respect to y. We can get a better idea of the partial derivative with respect to x using this following visualization. So we have the point AB in the xy plane fixed, okay? We can vary that point AB. So here I'm varying A. You could also vary B. This is where we want to evaluate the partial derivative with respect to x. Okay, and what are we allowed to vary when we're taking the partial derivative with respect to x? We allow x to vary. Okay, so what you see here, the green line is the ratio prior to taking the limit. Okay, so that green line is the secant line. Notice that you have a plane there. That plane is the plane y equals b, and y is not changing at all as we're taking the limit for our partial derivative with respect to x. Y is fixed at b while we're doing this. So let's go ahead and take the limit as h goes to 0. We expect that the secant line gets closer and closer to the tangent line. Okay, so this is similar to the concept of the derivative of a function of one variable, but notice that y is fixed at b. Now we could also then vary b and find the partial derivative at different fixed y's, right? So this is what happens when you change y. But still you're getting the slope along the x-axis, okay? That's what the partial derivative with respect to x gives you. It gives you the slope along the x-axis of this black curve, which is the intersection of the plane y equals b. So where y is equal to where y is fixed to b, and the graph of our function f of x. Okay, the graph of our function, of course, is the orange. What about the partial derivative with respect to y? Well, now we fix x to equal a, and we could vary which a we fix x at, depending on the point which we want to evaluate these partial derivatives. Okay, but once we fix x to a, all the varying now occurs for the partial derivative with respect to y. All the varying occurs along the y-axis. Okay, so we want to evaluate the partial derivative with respect to y at the point AB that you see over there in the xy plane. And green is the secant line. Okay, and let's see what happens when h is reduced down to 0. The green line meets the blue line, which is tangent to the graph. But tangent how? Tangent along the y-axis. Okay, so it's tangent to that to that curve that you get, which is black. It's composed of the intersection of the x equals a plane and the graph of the function in orange there. Okay, so you're getting the slope along the y-axis when you take the partial derivative with respect to y. And now you might be thinking, well, you know, why should we just look at the slopes along the x-axis given by f sub x, right? The partial derivative with respect to x, and the partial derivative with respect to y. Why look at just along these slopes along the directions of x and y? Well, we later on will talk about a generalization to this concept and look at changes 360 degrees around, okay, so that we're not just fixed on the x-axis and y-axis. But for now, we are getting the rates of change or slopes along the x and y axes using the partial derivative concept. Now, some notation that you'll encounter for the partial derivative, here you see, for example, the partial derivative with respect to x. It's written as f sub x there, sub x. Sometimes I'll be saying f sub x to denote the partial derivative with respect to x, and you're given the point in which where you're evaluating the partial derivative with respect to x. Don't forget that we're on the plane. This is a function of two variables, so the domain is on the plane. So you have to give it 2 points there where you evaluate the partial derivative. You also see it written this way. This curly d there is sometimes called del. So you don't have the hard d if you want to contrast that with the derivative. It's just a typical d, but no, for partial derivatives we use this del or curly d. Given at AB, sometimes you'll also see this bar where x, y is equal to the point AB, or sometimes you'll just see AB. And this is also a notation that's kind of common, especially in physics, is that you just use the del with a subscript x there to denote the same partial derivative with respect to x. And here, once more, it's worth emphasizing that as you take the partial derivative with respect to x, y stays fixed at b. And as you take the partial derivative with respect to y, x stays fixed. I emphasize this because it's going to help us a lot when actually taking derivatives with respect to with respect to the x or y variable. Okay, so here's an example where we're going to use the definition to compute the partial derivative of f with respect to x. At which point? At this arbitrary point xy. Okay? So our point, rather than using ab, which kind of helped to distinguish fixed variables from unfixed ones, well, now if we're a little more comfortable, we just leave it as xy. Okay? But of course, when you take the partial derivative, this xy is considered to be the point where you're evaluating the derivatives. So here is the partial derivative with respect to x at the point xy. We have this limit, okay, just purely from the definition. Now what does this mean? Well, we have this function here. What do we plug in for the x value? For the x value, we plug in x plus h, because that's just the definition. And how do you plug in x plus h for the function fxy? Well, that's just going to give you x plus h squared over here. So wherever you saw x, you just plug in x plus h. Over here, you just get x squared y, the function itself at xy. And we FOIL out the square. Okay, we get this term. And simplifying, notice now you get these cancellations here. Those cancellations are important because then when we divide by h, we get rid of the h here and at the bottom, and we are left with a h times y there. Now once we take the limit as h goes to 0, this term goes to 0, and this term just stays fixed at 2xy. So the partial derivative with respect to x of our function x squared y is equal to 2xy.